In this episode, we will talk about PixelHacker, image in painting with structural and semantic consistency.
Yeah, image in painting. It's a really fundamental area in computer vision, isn't it?
It really is. Kind of sits between straight up image editing and, well, full-on image generation from scratch.
Exactly. Like removing an object you don't want in a photo. That's a classic use case.
Yeah.
You want the background filled in perfectly.
Right. And, as these tools become more common, everyone just expects higher and higher visual quality. It's not just about filling a space anymore.
No, absolutely not. The generated stuff needs to feel completely natural, like it belongs there,
Yeah.
which means getting the structure right.
Things like texture, shapes, how objects relate spatially.
And the semantics, too.
Meaning like color consistency, making sure if you're rebuilding an object, it actually fits the scene.
Precisely. Logical correctness, basically. And this is where even some of the really advanced methods can stumble a bit.
Yeah, how so?
Well, with complex structures, tricky textures, weird shapes, lots of stuff going on, or subtle semantics, you often get, well, artifacts. Things look blurry or weird patterns appear, or the generated content just feels off.
Okay.
The PixelHacker paper actually shows some examples of this, where current methods struggle with things like tree trunks not lining up or water looking weird, railings breaking oddly, or just busy backgrounds getting messed up.
Ah, okay. So PixelHacker aims to fix that. Better consistency, both structurally and semantically.
That's the goal. And their main weapon is this new idea they call latent categories guidance, LCG for short.
LCG. And it's based on diffusion models.
Yes, it's a diffusion-based model, and LCG is really the core concept.
So what is latent categories guidance? How does it work?
The basic idea is to guide the whole in-painting process using latent features, specifically features representing the likely foreground and the likely background of the image.
Foreground and background features. Interesting. So how do they get those? Did they need special data?
Oh, yeah. They put together a huge data set, something like 14 million image mask pairs.
14 million.
Yeah. And the way they labeled it is pretty clever. Instead of trying to identify every single object type, they basically classified regions as either foreground, potential for like 116 different categories, roughly, or background, with about 21 potential categories.
So it's a broader classification, not this is cat, but this is likely foreground.
Exactly. They list the specific categories in the supplementary materials if you really want the details, but the key is that broad distinction.
Okay. And how are these categories used?
They use two fixed size embeddings. Think of them as compact summaries. One for foreground possibilities, one for background in the latent space.
Right.
And these embeddings, these latent features, get injected sort of intermittently into the denoising process.
The part where the diffusion model cleans up the noise to generate the image?
They use something called linear attention to feed these features in and guide the generation.
And they mentioned that during training, they don't actually tell the model, hey, the thing in this mask is a person, or it's a car, it's just foreground or background.
That's right. It's a key point. Everything in the mask is treated as either foreground or background during training.
What's the benefit of doing it that way? Seems less specific.
Well, it actually helps compress the representation for all sorts of different objects.
Yeah.
By focusing on just foreground versus background semantics, the model doesn't need to handle hundreds of specific labels for the masked bit. It simplifies things and potentially reduces the implementation cost, too.
Okay, that makes a certain kind of sense. Generalization over hyperspecificity. So let's talk architecture. They show it in Figure 1, right?
Yeah, Figure 1 gives a good overview. It builds on the standard latent diffusion architecture.
So what goes in?
You've got three main inputs. A noised image, the starting point for diffusion, then the clean mask showing what to fill in, and the clean mask image, the original with the hole already there. These go into a VAE encoder that's variational autoencoder to move everything into that lower dimensional latent space. Makes things more efficient.
And in that latent space, the LCG embeddings come into play.
Exactly. Those two fixed-size LCG embeddings, foreground and background, they use linear attention doing both the downsampling and upsampling parts of the UNet structure within the latent diffusion model.
And the embeddings are injected into the linear attention.
Yes, intermittently. That's how the model gets guided. It's where the interaction for structural and semantic consistency happens.
So the model is constantly getting these foreground-background hints as it refines the image.
Pretty much. Then, once the processing in latent space is done, the final features go through the VAE decoder.
Which turns it back into a regular image.
Right, the final in-painted image. And they also mention using classifier-free guidance, CFG, during inference when you're actually making the image. That's pretty standard for latent diffusion models, helps boost quality.
Okay, CFG. Got it. So this latent categories guidance, the LCG, section 3.2 and figure 2 seem to go deeper into how they actually construct this guidance. What was the thinking there?
Well, they were looking at prior work. Some methods use random brush masks, right? And those are
Yeah.
pretty good at learning structure, like textures and stuff.
Yeah, I remember Llama used those.
Exactly. But those random masks don't really give you semantic information, what's actually in the image. On the other hand, using segmentation masks gives you semantics, but just having a fixed set of object categories might limit generalization to new things.
So they wanted the best of both worlds, structure from random-ish masks, semantics from segmentation, but without being locked into a fixed list of objects.
You've got it. LCG tries to bridge that. It uses both kinds of mask information, but distills it down to just those two broad latent categories, foreground and background.
And figure 2 shows the different mask types they use to achieve this.
Yep. 4 main types during training. First, object semantic masks. Figure 2A shows masking out benches, for example. These get assigned to the foreground embedding.
To teach the model, this is what foreground stuff looks like in context.
Exactly. Reconstruct semantically relevant foreground objects using the background context. Second, scene semantic masks. Figure 2B shows an example. These go to the background embedding.
To help understand the overall background scene?
Enhanced background semantic reconstruction. Third, random brush masks, like we mentioned. Figure 2C. These also go to the background embedding.
Why background for the random ones?
The idea is to force the model to focus on learning structure textures, edges from the surrounding context when faced with these arbitrary holes.
Okay, makes sense. Learn general patterns.
And fourth, random object masks. Figure 2N, also assigned to the background embedding. This one's more like a regularizer.
A regularizer. To prevent what?
To stop the model from overfitting, basically. To prevent it from relying too heavily on the specific object semantic masks for the foreground and make sure it still pays attention to the general background embedding condition. Like, sometimes an object-shaped hole might still need background-like filling.
Right, keep it flexible. So they combine these somehow.
Yeah, they have a formula for the background mask. It's the scene mask plus the random brush mask times some probability, plus the random object mask times another probability. They call the probabilities PRAND and POBJEC.
And the foreground mask.
That's just the object semantic mask. Simple as that.
So the big picture is the model learns foreground patterns under the foreground embedding condition and background patterns under the background condition just from these masks. No text prompts needed during this LCG training.
Exactly. It learns through the learnable weights in the embeddings themselves, which is pretty neat. And then for inference, they can use that classifier-free guidance to sort of blend the learned characteristics of foreground and background effectively.
Okay, cool. Now, how do these LCG embeddings actually interact with the image features? Section 3.3 and Figure 3 talk about this structure and semantic consistency interaction.
Right. So this interaction happens multiple times during denoising, as we saw in the overall architecture. Figure 3 zooms in on a single interaction step. You have input features, lin, and output features, lout.
And the cue mechanism is gated linear attention, GLA.
Yep, GLA. They set another paper for that. It involves a few components: cheek, KT, VT, QT, REC, Saint, GLA. The cheat just refers to the token index, basically a position in the feature map.
Okay, so what's the flow?
First, you do self-attention on the normalized input features using GLA. This gives you self-decoded features.
The features talking to themselves, basically.
Kinda, yeah. Then, standard stuff, add a residual connection, add the original input back, and normalize again. And then comes the cross-attention step.
Ah, this is where the LCG embeddings come in.
Exactly. The self-decoded image features interact with the foreground and background LCG embeddings here.
Okay.
Finally, the result goes through an MLP, a multi-layer perceptron, to produce the output features, lout.
And you mentioned this happens multiple times, alternating self-attention and cross-attention.
That's right. Self-decoding, cross-decoding. And once those LCG embeddings are introduced via cross-attention the first time, all the following steps incorporate that guidance. It permeates the rest of the process.
So the foreground-background info sticks around and keeps influencing the generation. The paper gets pretty mathematical about calculating the GLA stuff. Can you give us the gist?
Sure. Basically, you compute query Q, key K, and value V matrices from the input features using linear layers, like in standard attention. Then there's this gating matrix, JAG.
GAG in GLA.
Right. It controls how much of the past information stored in an internal state, Saint, is kept versus updated. It uses sigmoid functions and stuff. Then the final output feature for a position, LOT, is calculated using these Q, K, V, and the state saint, plus some other transformations and activations.
So GLA is basically a fancy attention mechanism that lets the image features interact with each other and the LCG embeddings in a controlled, gated way.
That's a good way to put it. It allows for efficient processing while modeling these complex interactions needed for consistency.
Okay, let's switch gears to the results. Section 4. Looks like they really put PixelHacker through its paces.
They did. Tested it on Places2, Big Scene Dataset, and also Celeba HQ and FSHQ, which are high-quality face datasets, standard benchmarks for inpainting.
And they used that massive 14 million image dataset they built for the initial LCG training?
Yep. Pulled together from Coconut Large, Object 365 V2, Google Landmark V2, plus some curated scenes, about 4.3 million foreground pairs and 9.7 million background pairs. They used AlphaClip and SAM for auto-labeling. Huge effort.
Definitely sounds like it. And then they fine-tuned on the benchmark dataset.
Correct. And they were careful to follow the same fine-tuning protocols as prior work for fair comparisons.
Good practice. So Places 2 results first. Tables 1, 2, 3, and figures 4, 7. What did they find?
Okay, Table 1 is the Places2 test set, 512 resolution, pretty large masks, 40–50% removed. PixelHacker comes out on top for FID, that's fresh at inception distance, measures quality and diversity, and LPIPS, learned perceptual image patch similarity, measures perceptual closeness.
Better scores than things like Llama, LDM, Stable Diffusion, PowerPaint.
Significantly better. FID of 8.59, LPIPS of 0.2026. And interestingly, its zero-shot performance, without fine-tuning on Places2, was also really strong. FID 12.19, LPIPS 0.2100.
Wow, that zero-shot result really suggests the LCG pre-training taught it some very general things about images.
I think so too. Then Table 2 looks at the validation set, again 512 res, but with both large and small masks. Here, PixelHacker was very competitive, getting the best FID and UID scores compared to methods using similar amounts of training data. Some others used way more data.
Right, and Table 3, different resolutions.
Yeah, 256 and 512 resolution on the validation set. PixelHacker hit state-of-the-art at 512, even though it was mainly trained at that resolution. Shows it's robust.
And the pictures, figures 4 and 7, do they look better?
They really do, especially with those big masks. You can see PixelHacker keeps things looking coherent, structurally sound, semantically plausible, while other methods often show more artifacts or just weird results. Less jankiness.
Less jankiness, I like that. Okay, what about faces? Celeba HQ and FFHQ results in tables 4, 5, and figures 5, 6, 9.
On Celeba HQ, 512 res, table 4, again, state-of-the-art FID, 4.75, and LPIPS, 0.115. It shows the approach generalizes well beyond just scenes to faces.
And the qualitative figures, 5 and 9.
They show really clear facial features, minimal distortion, better structural consistency too, like avoiding weird patches of texture that don't belong.
Nice. And FFHQ, that was tricky, right? 256 resolution in table 5.
Yeah, FFHQ is tough. But even there, at 256 res, PixelHacker got state-of-the-art FID, 6.35, and LPIPS, 0.229, which is impressive since it was trained mostly at 512.
And figures 6 and 9 show it handles the complexity.
Yeah, they highlight realistic results, handling different lighting, complex backgrounds you often get in those more in-the-wild face shots.
So consistently strong performance across the board. Did they do ablation studies to see which parts mattered most? Section 4.5?
They did. Really useful stuff. Table 6 looks at the different mask types in LCG.
What did they find?
Basically, using all 4 types, object semantic, scene semantic, random brush, and the random object regularizer masks gave the best results. They all contribute something valuable.
So the whole combo matters. What about the embedding size? Did bigger embeddings help? Table 7.
Interestingly, not really. They tested dimensions from 20 up to 1024, but found that just using 20 dimensions for the foreground and background embeddings was pretty much sufficient. Going bigger didn't yield significant gains.
Huh. So you don't need massive embeddings to capture that foreground-background distinction effectively. That's efficient.
Seems so. And Table 8 looked at the classifier-free guidance scale.
The CFG strength.
Yeah. They tested scales from 1.0, no guidance, up to 4.0, found that a scale of 2.0 gave the best trade-off between quality and sticking to the input mask. So that became their default.
Good to see they validated those choices. Did they show any cases where it didn't work perfectly? Any familiar examples?
Yet Figure 8 shows some limitations. It can sometimes struggle with like super fine details or really complex repeating structures. Fingers were one example they showed where it wasn't perfect.
Okay, so it's not magic, but still an improvement.
Exactly. Even in those tougher cases, they argue it generally maintains better overall coherence than the other methods they compared against.
So summing up PixelHacker, the key is really this latent categories guidance, this LCG idea.
Absolutely. That's the core innovation. Guiding the diffusion process with these learned foreground and background latent features seems incredibly effective for getting both structure and semantics right, achieving that consistency.
And the results back it up. State-of-the-art performance across places too, Salive HQ, FFHQ.
Yeah, the experiments are pretty comprehensive and show clear advantages over existing methods on these challenging benchmarks.
It really is impressive progress. Seeing this level of consistency in painting, it makes you wonder, given these advancements, what kinds of new creative or practical applications can you envision for this technology? And maybe what do you think the next big challenges are for researchers in this space?